Now we're going to start using our Lewis dot structures to predict the shape of molecules, or we say the geometry of molecules. One thing I want to point out, because we kind of overlook this sometimes, is that anytime you have two atoms that are bonded, we'll call that shape linear. And so, I mean, that's simple, but sometimes we overlook that possibility because it's so simple. So it doesn't matter what two atoms that we call that linear. Anyway, this model predicts the shapes of molecules based on the idea that electron groups repel each other. So an electron group, it can be a bonding or lone pair. In other words, when I say it could be a bonding pair, it could actually be, so it could be a single bond or a double. It doesn't matter, or even a triple. A single bond, a double bond, or a lone pair, those are all examples of groups. And we're looking around the central atom for those. The idea is that you can't separate the two electrons in a single bond from each other, but as a group, they will repel other electron groups. Anyway, it's a way to think about it to make some predictions. And so we want to maximize the distance between those. Let's look at an example, and first thing I'm going to do is redraw this carbon dioxide because these are double bonds, but it makes it a little harder to look at when they're drawn with all dots. Okay, there's carbon dioxide. So how many electron groups are around the central atom? So a group means just a bond or a lone pair, and this is a double bond, and this is a double bond. So this one has two. And so two electron groups, if they want to repel each other, what they're going to do is be just how I drew it on opposite sides of that carbon atom. So we call this shape linear. And this is three atoms that are linear, but it's linear. And actually notice right here, we're talking about the electron geometry. So on this one, we're talking about these, okay? We're not talking about the location of the atoms yet. This distinction becomes a little more clear when we look at bigger ones. But anyway, so that's the electron geometry is linear because these electron groups will be exactly opposite each other because they repel. But then when we go to the molecular geometry, now we're going to look at atoms. And so now I'm looking at where the oxygen is compared to the carbon. And this is still in a straight line, so this geometry is called linear. So we already did our first one, and we have these in grouped by group. If you have two electron groups, then the shape of the molecule is linear. And like I said, you guys, if there's just two atoms, we call that linear as well. Okay. The next possibility is if you have three electron groups. So on this one, this is a single, and a double bond. There are three electron groups there. Okay. The electron geometry, when you have three groups, the furthest they can get from each other is to kind of go out like at a triangle, to go at opposite directions there, and the shape that you get we call trigonal planar. Okay, so that's this. We got our central atom, and these are the electron groups coming out from it. When we look at the molecular geometry, now we're going to be looking at the atoms. So now we're looking at where the atoms are. And no surprise that they are at the corners of a triangle as well. So for this molecule, because it has atoms in all of those places, it's trigonal planar as well. Okay, and you're going to see this is true. Anytime you have no lone pairs, then the electron geometry will be the same as the molecular geometry. Okay, here's where it gets different, is if you have a lone pair. So this one is actually like this molecule here. It has a lone pair, so it's kind of like a lone pair there and two atoms. This lone pair is drawn kind of big because that's really how it is. It really sticks out like that. Okay, so in this case, the electron geometry is still trigonal planar. All of these are trigonal planar. But on this one, when you look at the molecular geometry, you only look at the atoms, and now it's no longer a triangle. We call this shape bent. And the angle here is 120, so we say bent 120 degrees. And what I'm talking about is this angle here. Now to 4 electron groups. If you have 4 electron groups, the way that they can get the furthest away from each other is to be in a tetrahedron. So for our electrons, a tetrahedron, something like this, and actually it's drawn here a lot better than I can, but the electrons go out to the corners of a little pyramid with a triangular bottom. So the geometry of the electrons is called tetrahedral. Okay, and so those are the electrons. Now the molecular geometry depends on how many lone pairs we have. So again, here's our electron geometry is that tetrahedron. Our molecular geometry on this one, we're looking at the atoms for molecular. It has an atom on each electron group. So the molecular geometry and electron geometry are the same. Next, what if we had, instead of having atoms in all of the places, we had a lone pair on one of them. So here's our central atom. So like this. So now we have a shape for our, when we look at just the atoms, we have a triangular base, trigonal base. The central atom is lifted up a little bit, and we've got the lone pair pointing out the top. Because it's lifted up, it's not flat anymore. We are going to call this shape trigonal, but we call it pyramidal because it's slightly raised up. The next geometry is actually the geometry of water. Water looks like this. It has 4 electron groups, so electrons are tetrahedral. But its molecular geometry is like this. When we look at just the atoms, we have just this shape that's bent. And so this one's called bent. And the angle is different. This one is bent 109.5 degrees.